Example 4.3.2. Setup for this one says, you would like to start a scholarship at your alma mater. You expect to earn 8% interest per year on your investments. How much must you deposit today so the scholarship can pay $10,000 next year and have the payments increase 4% each year in perpetuity? All right, we've got a time value money problem, so we're going to use our familiar three-step process where we start by mapping out the cash flows and labeling all the information that we know so that we can figure out what type of cash flow we're dealing with and therefore know what tools we have available to evaluate it. All right, so with this one, at time period 0, we're looking for what we can deposit today in order to create this scholarship. So we don't know what the cash flow at time period 0 is. We do know that whatever we deposit, we expect to earn 8% interest, and then we expect to use that 8% interest to create or to generate $10,000 worth of interest that we can then pay out as a scholarship. So 1 year from today, we want to be able to pay out $10,000. And then 1 year from that deposit, we want the next payout to not be $10,000, but to be 4% larger than $10,000 so that we can compensate the scholarship recipients for increases in food costs, in textbook cost, in tuition. We want to build in some measure of protection against general price rises. So that means the payment 2 years from today is going to be 4% larger than 10,000, or that's 10,000 times, we can say 1 plus the growth rate to grow at 4%, or in this case that's 1.04. All right, so 10,000, we can type it in if we want, just going to be 4% times 10,000, just so we can see how the math works out here. All right, so there's going to be an extra $400 or an extra 4% on that cash flow. So that means the cash flow at the end of year 2 is going to be $10,400. And then the cash flow 1 year after that is going to be that original $10,000 and then 4% larger again. So with this one, we could either take the $10,400 and then multiply it again by 1.04, or just to keep the pattern the same, we can take that same $10,000 and we can multiply it by 1.04 squared to multiply by 1.04 twice. All right, so times 1.04 again. So that means the payment 3 years from today will be again 4% larger, or $10,816. All right, and it says we want these payments to last in perpetuity. So this pattern is going to continue forever. So we'll just do an arrow and our little infinity sign just to show that it goes on forever. Okay, we've completed step 1. We've got our cash flows mapped out. We have all the information we're given in the problem. Step 2 is to identify the type of cash flow that we are dealing with. Well, again, we've got a big hint in the problem. It says perpetuity, and if I look at my cheat sheet for the different types of cash flows, if I look under perpetuities, I see I have 2 types. I have just a plain perpetuity, which is where we have a level cash flow at regular intervals that lasts forever. That's not what we have here. The payments are actually increasing at a set rate. Well, I can see an example of that in the second timeline, where these particular cash flows are growing at 3%, even though ours are growing at 4%. It's still the same general pattern. So we have a cash flow at regular intervals that is growing at a fixed rate. Well, that is a growing perpetuity. All right, so we'll go ahead and identify that. We'll label it as a growing perpetuity. Well, once we know that it's a growing perpetuity, that allows us to know which tools are available to us to solve the problem. And in this case, it's just formulas, but if there's formulas and time value money keys involved, if we're going to use the formula, there's a long list of formulas associated with these problems. But if we've identified the type of cash flow that we're looking at, we've narrowed it down to at most 2 formulas. Right? If we're dealing with something like an annuity or a lump sum, we could be solving for either present value or future value. And those are really the same formula, just rearranged to solve for one or the other. In the case of a perpetuity, or a growing perpetuity in this case, there's really just one formula. There's the present value of the perpetuity. It doesn't make a lot of sense to talk about the future value of a perpetuity because the cash flows last forever. And when we talk about future value, we're usually talking about the terminal value, so the value at the end of the timeline when the cash flows end. So we really just talk about the present value of a perpetuity. All right, so we've got one formula here. That makes our lives simple. There's only one thing that we have to use for this, and that is the present value of the perpetuity. And I'm going to use subscripts to keep track of the timing. I'm looking for the present value as of time period 0. So I'm going to say PV sub 0 to keep track of that timing. And the formula for that is the present value at some period, here time period 0, is equal to the cash flow one time period later. In this case, that's 1 year later. So I'm going to write CF sub 1 divided by the interest rate minus the growth rate in those cash flows, where R is the interest rate, just like always, and then G is the growth rate in the cash flows. All right, so let's plug in the information from this problem. PV sub 0 for the present value at time period 0 is equal to the cash flow 1 period later. In this case, that's 10,000, divided by the interest rate, which is 8% in this problem. As a decimal, that's 0.08, minus the growth rate in the cash flows. That's the 4% larger that each cash flow is. And as a decimal, 4% is 0.04. So we're going to do 0.08 minus 0.04. And we put those in parentheses because we want to do that subtraction first before we do the divisions. We want to make sure we follow the correct order of operations. In fact, just to be sure, we'll go ahead and write that step out. So the present value of 10,000 divided by 0.08 minus 0.04 is going to be 0.04. All right, and if we plug that in, that's 10,000 divided by 0.04 is equal to 250,000. All right, so that means if we were to deposit $250,000 today at time period 0, then that initial deposit of $250,000 will earn 8% interest. And that 8% interest is going to be a good bit more than $10,000 in this case, but we'll scrape off $10,000 and pay it out as a scholarship, and that'll leave the original principal in plus a little bit more that will then earn 8% interest again and allow us to pay out a little bit more at the end of year 2, $10,400. And so every year we'll leave a little bit of interest in there so that we can earn a little bit more interest than we would on just the original principal to allow that payment to grow each year. Right? So this is where we can see that timing difference in the formula, where the formula gives us the present value as of one period before the first payment. And that's because of what we're creating here. When we create the perpetuity, we need that initial deposit to earn interest for one period so that we can then pull that interest off and pay it out and leave the principal untouched. So it's important to recognize that timing difference with both the present value perpetuity formulas, and it's also at play with the present value of annuity formulas, where the formula is always giving us the present value one period before the first cash flow that we plug in. But that's it for this one. All we can really use is the formula. The time value money keys on a financial calculator don't know how to deal with an infinite series of cash flows. And then there's no real spreadsheet function for a perpetuity. We would just be having the spreadsheet do the calculation for us that we plugged in by hand here. So that's it.